Okay, thanks everybody for coming this morning. Today we're very excited to have Geoffrey Compére. He's going to tell us about Kerr Geodesics and self-consistent match between Inspiral and Transition-to-merger. So take it away, Geoffrey.
Thank you, Daniel. So it's my pleasure to be here in my office with you. So we're in between 3 different time zones, I heard. So I don't know if actually good morning, good afternoon, or good evening for the 3. So here is the outline. I will talk about 2 pieces of work, one done with Yan Liu and Chang Long about the Kerr Geodesics. And that will be the beginning of my talk. And I will move towards the self-consistent match between Inspiral and Transition-to-merger, which was done with Lorenzo Kuchler. And we have one paper published and the other one will be published next week on the archive. So let me start with a nice video as a, well, just for the beauty of it. So here is a simulation of Sagittarius A star, well, it's supermassive black hole at the center of a galaxy. Here are all the stars that have been measured, so the different trajectories of various stars. And it's been a lot of effort in the well, the last several decades to obtain these trajectories. And so these observations, in fact, they are totally matched with geodesics of a Kerr black hole, where the Kerr black hole will be Sagittarius A star, that's the center of the galaxy, at the center of the galaxy. So if you can compare this to a plot from the Kerr Orbit visualizer of Niels Warburton, from the Black Hole Perturbation Toolkit, it's totally accessible for everyone to use it. And you find according to various parameters, you put in various trajectories such as this one. So the equations governing the Kerr geodesic equations, so the time Kerr geodesic are first order differential equations. So they can be put in one slide. They've been solved numerically since the 70s, but it's interesting to obtain analytic forms, especially for doing perturbation theory. So that's what one of my main motivations is to look at inspiral motion, including back reaction and gravitational wave back reaction on the trajectory. And when you do perturbation theory, you better know very well first your 0th order solution. So so let's see what we can say about this geodesics. Please do not hesitate to interrupt me also for questions. Huh? So there's a lot of history. So the start is the Kerr solution in '63, and then Carter that found the 4th constant that allows to have 4 constants of motion: the mass, energy, angular momentum, and the Carter constant. And then the motion reduces to can be integrated, so it's UV integrable. Then there was an analysis of bound geodesics by Wilkins that is well known. It has been extended by Schmidt, Fujita, Ikeda, just to mention them. A lot of work has been done by Bardeen in the 73, and he studied mainly the Equatorial time-like geodesics and null geodesics. And further work extended that, especially Chandrasekhar in '83. Negative energy orbits are interesting because they occur for Kerr within the ergo region, and they've been classified by Kontopoulos in the 80s. And then there's further work. Interestingly, Minot found out to decouple the radial polar motions. It's pretty straightforward. You have to introduce a Minot time. Then much later, the near horizon, near extremal Kerr orbits were looked at and I will discuss them a bit later as well. Then the latest development is to find explicitly real, fully explicit, initial dependent analytical solutions in terms of elliptic functions. And so this program has been well performed for radial and polar motion for time-like bounded orbits already some time ago, and summarized nicely by Martin van der Meent. And here in the room, you have Daniel and Alex that produce these forms for generic polar motion for null or time-like orbits, and generic radial motion for null orbits. And also this near this extrema limit was also solved. Oh, yes, there was a 2 missing, of course. It's 2020 here. 2020, sorry. So the last step for this program is with the radial motion for generic time-like orbits. And so it turned out to be a very complicated problem. So here I would just like to do already a first step in that program is to explain what the phase space of this radial motion. So let's first talk about the polar motion for a minute. So the polar motion, you can write it this way. So if I call z the square of the cosine of the angle of the polar coordinate, the potential v is quadratic in z with these coefficients. And it has 2 properties. So z goes from 0 to 1. So at 0, you find q, and at 1, you find minus s squared. So when q is positive, you always have a lot of motion because v goes from a positive value to a negative value, and you will cross the horizontal axis once, and so you will have a polar motion that will exist. V will be positive in some region between 0 and the first root. Now, when q is negative, you have to look a bit what kind of parabola you have here. So either you have a parabola that goes upside down or downside up. It depends on your parameters. On e squared minus mu squared. Mu is the mass and e is the energy. So if you have a parabola that goes up, so when e is between 0 and mu, then there's no way you can have a log motion for q negative, because you have 2 negative values and the parabola that will be even more negative. So that's ruled out. So this is why you have a bound q bigger than 0 for when the energy is less than mu. But when the energy is more than mu, then you have to look at the details, and then you find this bound. So that bound reduces to a bound obtained by Samuel Guerra and Alex Subsaska for the null case, where mu is 0. So within the ergo region, you also have interesting constraints on the motion. So the ergo region is defined in Boyer-Lindquist coordinates as the radius given by this quantity. So from now on, I will use the mass and of the main Schwarzschild black hole and the mass of the probe particle 1. Sorry, the Kerr black hole. I mean the mass of the Kerr black hole. So some features. So these features that d mu t is path directed and gt phi is negative is immediate from the metric, and implies that the motion is such that the time, the velocity is positive. So the time flows on the proper time. It's positive, and d phi over d tau is also positive. So you always go along the direction of the angular momentum. The motion goes along the motion of the angular momentum, direction of the angular momentum. It can be 0 at the ergosphere, so you can just co-rotate exactly at the ergosphere, but inside the ergosphere you need to continue to rotate further. So, explicitly these constraints are given here. So, so there are a couple of properties you can directly see from these two equations, these two inequalities. So first, at the ergosphere, if you just plug the radius of the radius inside of this condition, it's violated when E is negative. It's immediate. You don't see it here, but well, you have to plug it in. So no motion with negative E takes place strictly inside the ergo region. A second property is that these constraints are explicitly odd if you flip the sign of E and L. So there is a central symmetry in the phase space of analog motion within the ergo region. simply because of this symmetry. Then the third property that you can immediately see is that for orbits that reach the horizon, so the last term will dominate because the delta goes to 0 at the horizon, so this term dominates. So it means that this bound has to be obeyed. And that's in fact a special case of the second law of black hole thermodynamics. So this is the law of thermodynamics. The entropy has to increase. The entropy is given by this quantity. And if you have an orbit that reaches the horizon, it plunges into the horizon, so the mass of the black hole will be changed by the energy of the particle, and the angular momentum of the black hole will be changed by the angular momentum of the particle. And therefore, if you put this term on the left-hand side, on the right-hand side, you find that you have a lower bound on L. So the L will be lower than this bound, and that bound is in fact exactly this one. So, so the plunging orbits are constrained by the second law of thermodynamics. Note that bounded orbits are not constrained by the second law of thermodynamics because they don't reach the horizon. So this is only for the orbits that reach the horizon, where this term dominates. But then if you play a bit with these equations, you can find various types of other constraints that will allow you to rule out specific motion inside the equation. So, but that requires a detailed treatment. So let me just give you the results. So here's for the polar motion. So there are 4 classes of polar motion. It's pretty, well, it's fairly simple to derive these 4 classes. What is not simple is to derive explicit and Liken formula for them. So you can read the paper. But basically we have the liberating motion, so pendular motion around the equator. There is a special case where the energy is exactly the mass, because then this term vanishes and the quadratic becomes linear. So then the formula simply changes a lot. And then you have the vertical type motion, so inside of the north sphere or the south sphere. And the vertical motion occurs for negative Carter constant and for energy larger than 1. And then there is this very special case when the Carter constant is 0. So when the Carter constant is 0, usually we consider equatorial motion occurring on the plane of the equator. But if you start the motion with a polar coordinate which is not at the equator, then you would just have this kind of motion. So it would just flip once. So we call it equator attractive. So that's the classification. Now for radial motion, it's much more complicated. And why is it complicated? Well, because now the potential, this radial potential, is a quadratic function of the radius. So if you want to understand the motion, you want to understand the poles, the zeros of this, sorry, not the poles, the zeros of this radius, of this radial potential. And so to understand where are the various zeros, depending on the parameters, you have to obtain the discriminant of a quartic. And the discriminant is in fact quintic in the Carter constant. And it's a polynomial of degree 10 in angular momentum and degree 12 in the energy. So then you want to understand that discriminant. Actually, there's a way to do this. And so to summarize this, I will introduce a notation which I find convenient. I want to use it's like it's inspired by quantum mechanics, but I find it just nice for writing the roots. So the outer horizon will be a vertical bar. The radial infinity will be this bracket. The allowed region where big R is positive, it means allowed motion. It will be R is positive will be a plus. R negative is disallowed region. And then the roots, I will deal with them like this. So there can be a root that is at the horizon. So root touching the horizon is also a case that exists. So when you have a simple root, it means that you have a turning point because the radial derivative with respect to proper time goes to 0. So it means that you have a turning point. If you have a double root, well, you have two different things that can happen at the double root. Either you stay at the double root, so you have a spherical orbit, or so I say spherical because I don't know about the polar motion, and you can go you stay at the same radius. It can be spherical, or it can be equatorial, or you have orbits that approach this double root, and so they will approach it with an infinite time, because the velocity will asymptotically go to 0 because of the double root. It will give you an asymptotic motion towards this double root. And then you have the special case, which is a triple root, and it's called innermost stable spherical orbit. Okay, so after the analysis, we came up with the list. So I mean, this list has been known since a long time, but somehow was never really written like in a closed form. So here's the list of possible root structures. So if you take, for example, that root structure, what does it mean? It means that you have a geodesics that can go from the horizon to the turning point and back to the horizon. So that's one geodesic class. If you see that root structure, you have this bound motion between these two roots that bounce back and forth, and then you have this plunging motion here. So that's two geodesic classes, and so on. You can never have a fourth root. It's only maximum is a third root. Okay, so now the question is how you write the phase space for this. So here is just a plot for the radial motion in the equatorial plane, where it's possible to draw it. You have the Carter constant, which is a third dimension here, so you might need to write this in 3 dimensions. So instead, we wrote different cuts for various values. So here is an example of what it looks like. You have, for example, here, that will be the one that will interest us. You have the stable circular orbits here. So those, you have here spherical orbits that are stable because there's no motion allowed on either side. And here you have the innermost stable spherical orbit, which is prograde, so positive angular momentum. You have the retrograde one, negative angular momentum here. And in here, in this region, you have plunging orbits, because you have these orbits that go from the horizon and that go back to the horizon. And that part is forbidden with the various the constraint on polar motion. Okay, so I'm not going to detail any of this, but if you have questions, please ask. At E=1, you start to have the orbits that can reach infinity. Huh? So the motion is allowed in the asymptotic region. When E is less than 1, you have the motion that is not allowed. That's very simple. It's because the leading power here, the radius is positive for large radius or negative for large radius, depending on this, if the energy is bigger than mu or not. Okay. So just to mention a couple of outcomes of this analysis before I switch to the Inspiral. So in the ergosphere, we found like 6 different particular value of the angular momentum, which has special meaning. And I don't know if they are of astrophysical interest or not. But the first here is just what they mean. So within the ergosphere, I will introduce this notation now. Parenthesis means that we reach the ergosphere. So the full root structure reaches the infinity, which is all the way to the asymptotic infinity, but we just truncate it and look at the ergo region now. So I will, for all these root structures, you have to look where is the ergosphere. So you need to understand where is the ergosphere, and that depends on the value of the angular momentum to know where is the ergosphere in all these quantities. So after analysis, you find various cases, and that depends on the value of the angular momentum. So for the case of when you're lower than this quantity, this is the kind of root structure you're inside the ergosphere. And then at that value, actually the photon orbit arises within the ergosphere. It crosses the ergo region. It crosses, sorry, the ergosphere, so it occurs within the ergo region. And then you start to have time-like bounded orbits, time-like spherical orbits, I'm sorry, time-like spherical orbits inside of the ergo region. Because for infinite energy, these kind of spherical orbits become the spherical null orbits. So they become that do not occur for this lower value rate. So that's what's happening here. And then if you increase the angular momentum, you have more and more type of orbit that reach the ergo region. And then let me just mention here is this value is already is a bit borderline astrophysically, but it's still maybe possible to reach it. And in that case, this is the most complicated case. You have the most interesting structure within the ergosphere. And you have particular bounded orbits, time-like bounded orbits that are there. So now, if you look at the very large angular momentum limit, you are in that case. And if you zoom close to the horizon, now you can ask the question, what is the root, this root structure within the near horizon region of near extremal Kerr? You can find it as the limit of that diagram, because now you ask, this near horizon region of Kerr, where does it occur here? So let me remind you that this is something very specific that occurs in the near extremal limit. This was observed already by Barley, Tukowski, and Press in '73. So there is really a throat that opens up close to the horizon of Kerr, and the spatial distance between a point outside the horizon and a point very close to the horizon diverges to infinity in the extremal limit, and you can identify, in fact, precisely the kind of geometry that occurs in this limit. If you zoom close to the horizon in appropriate coordinates and you take the limit, you find this near horizon geometry that was derived by Barley and Horowitz in '99. So now we can take this near horizon limit and see what kind of orbits we find here. So this is now the notation for the end of the near horizon region, and then you go towards the ergosphere, and then you go towards asymptotic infinity. And here is the near horizon region, because you have these two different regions here and here. And here are the kind of plots you obtain. And they match previous plots up to one difference. Actually, in previous analysis, there was one region of deflecting orbits that we call now, with respect to its root structure, that's a bit extended with respect to what we thought before. But except that, we will produce all the known results. And just to mention, there is an interesting business you can do with these orbits, which is conformance symmetry. So if you use the Kerr black hole has two symmetries, two killing symmetries, but the near horizon region has SL2R symmetry. So there's a larger group of symmetries, and therefore the various geodesics can be mapped using the symmetry to each other. And so that was started already with the work of Achilleas and Shara, Adar, and Strominger. And here is the summary of what you can do with it. So in fact, all these orbits, you can relate them to each other. You have three different conformal classes of orbits. So if you use all the possible symmetries, SL2R, the finite conformal transformations, and the various flips you can have, so various types of flips, discrete flips, then you can relate all the orbits within each class to a spherical type of orbits. So all orbits belong to one of the three symmetric classes of spherical orbits. And that's an interesting feature for that has some applications into generation of gravitational waves inside of a near horizon of Kerr. Okay, so that ends the part on geodesics. Do you have questions on this part? Yes, Shar? I can't hear you.
Yeah, hi, Geoffrey.
Hi.
I wanted to ask about that point you said about the second law of thermodynamics, the constraint you get on geodesics falling into the horizon.
Yes.
So is that related also, could that be related also to the overspinning problem? And does it also happen like for black holes in ADS? Is there some holographic interpretation of that?
Yeah, so this is so I would say this is a direct consequence of if you really look at the first law, we know first law is the second law a priori is true, And then you use this substitution, so you have a direct constraint. This constraint is true a priori in any spacetime, in ADS, and the interpretation of this constraint, if you follow the holography, we just say that the entropy of your safety has to increase as well in any process. So that's always true. Now the consequences of this on the classification of possible geodesic motion, and that's you have to do the analysis, I guess, case by case. It's related to the overspinning problem, because it means that the angular momentum can never is bounded. So to overspin, you would need to put an angular momentum which is really, really high to overspin the black hole, and actually you cannot do it. Your angular momentum is constrained. So that's part of the solution of the overspinning problem.
I see. Yeah, but okay. I thought that somehow you need to have like just looking at geodesics with no back reaction is not enough to solve the overspinning problem, I thought.
Yeah.
Right?
Yeah. I didn't follow that literature enough. Yeah, indeed there are. Yeah, I agree with you. There was. Yeah.
I mean, of course, now we have.
It's not a sufficient condition; it's just necessary. But you need much more. Yeah.
Right. Okay.
Yeah, I don't know what are the rest of the constraints.
I guess to sharpen Shahar's question again, is this bound that you derive just from thermodynamics sufficient to exclude all, leading order without self force taken into account overspinning orbits? Probably not, right?
No. So I have actually already. You see already this bound here. It's stronger condition than this one, and it comes really. These constraints are really the real constraints. So these two, and these constraints are really complicated because there is theta motion. It depends on theta and r, and the motion depends on both theta and r. And the motion is solved by elliptic functions, so it's really in a non-trivial condition. And that's more, you already at the equator, you have more stringent condition than that one, And we derive several other more stringent than these ones as well from these conditions. But it's still not totally solved. So we did not finish to solve we don't have a proof that we have a more stringent condition for any polar type motion. Because to resolve these two conditions is hard. Yeah, maybe that's the right answer.
Thank you.
Okay. So let me move a bit to the next topic. So my main motivation here is LISA. So the data for LISA mission will be expected in 2036. So far we don't have enough modeling for extracting for comparing the data with the prediction of general relativity. So it's a challenge to already generate correct waveforms in the case of extreme mass ratio in spirals, which means that you have two binary black hole merger where the ratio of masses is very high or very, very low, depending on which ratio you look at. So there's a standard methods to solve the two-body problem in general relativity. You have the numerical relativity, which applies for comparable mass ratio and for small distances, because you cannot model it for a very long time, and if you cannot model large separation of scales. And then you have the post-Newtonian methods, which are valid if you are a very large distance, so that you can have the small velocity approximation. And then you have these methods called the perturbation theory and self-force, which are applicable for large mass ratio. So those are the methods that we look now. And then you have the effective one-body methods, which try to put them all together into a consistent formulation. So the black hole perturbation theory method is it consists in expanding the metric starting from Kerr, from the geometry of the large black hole, which is this geometry of the large black hole, and then you look at the probe mass on it, and you look at different perturbations, and these perturbations will obey. So in Lorentz gauge, in a harmonic gauge, or the Doppler gauge is written like this. and it's sourced by the motion of the probe particle. So this motion itself will depend on the geometry and on this back reaction. So this is really a coupled problem. You have to evolve at the same time the metric and the trajectory. So what's the equation also for the trajectory? The trajectory obeys the so-called Mizata-QY equation from the authors. And this is a forced geodesic equation. And this forced geodesic equation takes this form. You need to compute the so-called tail part of the perturbation. And the tail part of the perturbation is defined from the retarded Green function of the wave operator of the first order Einstein field equation operator. So if you know this retarded Green function, you know how to compute this tail metric, and from there and the velocity you can compute this equation. So numerically it's a bit hard to do because you have to solve at the same time the motion. So you have to evolve at the same time the geodesic and solve at the same time for the Einstein field equation. So the problem I'm interested in here is the simplest possible problem you can imagine is the quasi-circular inspiral and the transition-to-merger motion. So this is what's really happening. And once we include this back reaction effects, so a particle will actually emit gravitational waves, and so it will, its motion is not going to be only the circular motion, which I'll depot using my favorite notation. You have the circular orbit here, and then you have some mu correction depending on the mass ratio. And so when you emit gravitational wave, you slowly lose angular momentum, and so it will go in spiral. And then at some point, it will approach the last circular orbit, and then the circular orbit will not exist anymore, and you will go towards a plunge, which is denoted with that diagram. And the plunge quickly goes into the central black hole. The main observables for gravitational waves actually is in that region, because that's where it's the strongest gravitational waves. So what I would like to model now is the inspiral and the transition close to the ISCO. So here is just to link with the previous part of the talk. Here is what you do in phase space. So you are in one of the circular orbits here, and then any forced geodesic motion is locally tangent to a geodesic at any proper time. So what you do is that you go from one geodesic to another one, where you just change the angular momentum and the energy. And so what you do in the spiral is that you follow this line. You follow the stable circular orbit line. So you diabatically go here, and then you reach the innermost stable spherical orbit, and then you go into plunge mode, where you have this kind of orbits here, plunging orbits. Okay, so let's start to derive this. So I will look only in the equatorial plane. So I want to know what are the equations for equatorial forced geodesics. So I'll start with Kerr, parameters M and A. No inclination, no eccentricity. I will look at the quasi-circular motion, simplest case. So the motion is determined with this position. So T, the Breuer-Lindquist time, the radius. I'm at the equator, and the phi is just the integral of the angular velocity, which is a variable of my problem. The velocity, well, I take the derivative with respect to proper time. I will call that u, the redshift, and the derivative of the radius. And I take the derivative, so this integral goes out, and I have u times omega. Now, a field redefinition is useful because we are looking at the quasi-circular inspiral. So there is a small deviation from the circular geodesic angular velocity. So the circular angular velocity is given by this formula. S is +1 when it's prograde, and it's -1 when it's retrograde. And so I will look at this parameterization where delta is a small deviation. So these are two equivalent formula. So I will describe the motion in terms of R and delta. M is scaled away from the problem. So here are all the equations. So you have the radial equations. You have the first order and second order forms. The self-force appears in the second order form, but not in the first order form. Then you have the time and phi components of your fourth geodesic equation. You can rewrite them in first order form if you introduce the angular momentum and the energy. And then you have the normalization of the four velocity. And it just, in fact, you can solve it in terms of the redshift. It just tells you what the redshift is in terms of the rest. And you take the time derivative of this equation and you obtain the orthogonality of the force with respect to the velocity, because then you get acceleration times velocity, and acceleration is the force. So you get directly this equation, and that gives you a constraint on the flux balance laws. So the flux balance laws have a constraint with respect to the radial self-force, which is also called the conservative part of the self-force. And the equation imply consistently that A does not change. So the A at the location of the particle does not change, even though the angular momentum of the black hole will change with time because of the change in time because of the absorption of gravitational waves. The A that appears in the equation does not change, the A at the location of the particle. So that was a subtlety that we took some time to understand. The way you solve this is you first solve the quasi-circular and spiral. So the standard methods were done by Flanagan and Hinderer in 2000. And you introduce a slow timescale expansion. So you introduce, you define a time which is eta times proper time, and you call that slow time. And then you make expansion slow time of your equations. So it turns out the range of validity is all the way to the ISCO in a region close to the ISCO. So you break down at some point when you get closer to the ISCO. The ISCO transition is modeled using a transition to plunge to merger motion in the transition timescale expansion. So now tau star is the time where you reach the ISCO, and I will expand around that. So I define a new time scale, which is the transition time scale. And I can prove it if I have time, but this is the range of validity of the transition time scale. And it's a region in here. And there is an overlap between the two, which is given by this. And therefore, we can use the methods of asymptotically match expansions to find the full motion. So, so in the last 20 minutes, I will just go through the derivation. I'm sorry, it's a bit, there are many formula. I will try not to explain the formula, just explain the philosophy, because I realize it's a lot of formula. But interrupt me if you want. The methods of yes.
Can you give us some intuition? Where did the 1/5 come from?
Oh, yeah. Let me try. Yeah, there's no intuition really about the 1/5. This is really, you have to make the expansion of your equations, and then you find you adjust you find that 1/5 is the right thing so that you have coupled equations. If you put a different coefficient, you find trivial equations that are saying you that your initial ansatz is just zero or inconsistent. Then that's the only one where you get consistent equations. So it's mathematically correct. Just so the 1/5 actually, this is another paper that I'm not going to talk about, but in a very high spin limit, actually the 1/5 is not true anymore. So you have a different scaling that occurs because actually the geometry changes. And then you have different scaling. So if you want to read about that, there is a paper I did with Caroline Jonas and Quinten Franzen. But here I'm looking at the standard spins. And this is that's 1/5 was found by Ori and Thorne in 2000. Okay, so the way you do the slow timescale expansion, so actually it's 2008. Yeah, it's only wow. It's very recent, huh? 15 years old. So, well, very recent. I'm not sure, but more recent than that. So here is the expansion. Any quantity has a zeroth order value, and then you have higher and higher perturbations. And you can expand everything you want: the radius, the deviation from quasi-circularity, the angular velocity, the redshift, the energy, the angular momentum, any quantity has this kind of expansion, and the self-force. And the self-force starts at eta, because that's where you have the first change of the geodesic motion. So now here is how you solve the equations. So you take part of your equations, you solve them, you find them as, you know, this is part of the solution. You find these conditions, which means that it's quasi-circular. So and you can check quasi-circular because the radius decreases very slowly with respect to phi. Then you solve the other equations and you find an algebraic solution. That's the only thing you need to know. It's algebraic. And there's one of these two flux balance law that you solve. The other one is automatic because of the quasi-circularity condition. The two of them are equivalent. And so you just solve one and you find one differential equation for the radius. So that's the only differential equation that you actually have to numerically solve. The rest is algebraic. And this differential equation has a pole, D. D is this equation, and it's singular at the ISCO. So it's exactly 0 at the ISCO. So that's why the slow timescale expansion breaks at the ISCO, because of this pole here. So these equations were nicely derived by Adam Pound and his student, Jerry Miller, last year. Now if you can go higher, so post-adiabatic, and everything is the same, you algebraically solve. You need some input about what the cell force is, and then you find some operator, one single differential equation, where which involves part of the cell force, the part which is linear in the variables you try to solve, R1, and the other part appears on the right-hand side, on the source. And this is all the equations exactly. So it still fits in one slide. If you go to next order, then it doesn't fit in one slide anymore. You have to expand the cell force. I'm not going to skip this because it's really technical, but you have to expand a bit the cell force, and this is the kind of equation. And it's only part of the equation because you have plenty of coefficients here that you have to actually expand. So this is typical of perturbation theory. It gets really, really ugly very quickly. But the main lesson is that you have one single differential equation at each order. The rest is algebraic, is totally solved. You just have to solve one differential equation. And the left-hand side here is exactly the same at every order. At second order is the same as this one. It's exactly the same. The only thing that changes is the source. So you just need to compute what the source is. So that's the lesson. Okay, so then you need to numerically solve this.
Can I ask a question?
Yes.
So adiabatic, the expansion here, you call it post-adiabatic. Is it equivalent to expansion in the mass ratio?
Yeah. So it's a mass ratio expansion. It's an expansion in the mass ratio at fixed slow time.
Okay.
So you fix slow time, which is this one. So tau tilde. You express everything in terms of tau tilde, and you make the expansion at fixed tau tilde in eta.
Okay. And
then the other motion will be an expansion in eta at fixed S, which is a different expansion. Yes.
I see. And from a practical perspective for creating gravitational waveforms, how high do you need to go?
So for LISA, there's been analysis for LISA. Where's my LISA thing? Yeah. So, well, you have to go to a post-adiabatic order, and that's sufficient. The reason is that you can see the scaling with eta, and if you have a small, you want to have at the end of your Inspiral that the angular. Let me try to see if I can do the argument again. You want that this quantity, which is the phase, which will be related to the final phase of the gravitational wave, is accurate up to 1 radiant. And then you follow the scaling of this, and it scales like 1 over eta. And so you need to go to second order so that you have order eta 0 correction, eta small. So you need to go to post-adiabatic order. And that's enough. But now there's a second motivation, which is actually to try to use this for equal mass ratio binaries by going to high enough order and then resumming. And then you want to actually understand the full structure, and then to be able to put that into EOB methods, explicit one-body methods. So that's another motivation here. So actually, maybe it's going to become the main motivation, because it's if you can do really a nice effective one-body method, then you just solve the entire problem. So that's also part of the motivation.
You can presumably presumably you can use these coefficients to calibrate your effective one-body model.
Exactly, yeah. So yeah, because we want to calibrate it using all the things you have, and so it has not been calibrated so much using self-force methods so far, but there's potential to develop the self-force methods enough to calibrate further the EOB methods. Yes, exactly. So that's my hope as well. Now I didn't even finish the Inspiral. I have only 12 minutes left, but let me just give you the asymptotic solution here. So if you go towards the ISCO, I need to know, to do the matching procedure, I need to know what's going to become the behavior. And I will skip the details, but mainly you can solve it. You can actually find the asymptotic solution. You need to make an expansion close to the ISCO. So I call R0 not the value of the radius at the ISCO. And you make expansion close to that. So you have to resolve the pole where your equation start to break down. And you resolve that pole, and then you find an expansion close to the pole, close to R0, and you solve it, and then you find that you have a consistent solution in half integer powers of the proper time. And that's interesting. So it's a singular type expansion. It's not the Taylor expansion. It's a singular type expansion. You have half integer powers of tau tilde that occur in this solution. So then the leading order solution is solved exactly. So that was actually done already by Ori and Thorne in 2000, and then developed further with Kesden, the work of Kesden, in 2011, I think. But we did it in much more detail, and including the cell force, the radial cell force, because that was not done before. So we want to be systematic and include all cell force effects. So let me just skip a bit this because it's a bit tricky to explain everything in detail. But the first order, this is the post-adiabatic solution. So the only thing you really need to understand is the differential equation. So you can make an expansion of your differential equation close to the ISCO. And then you find that you have more and more singular structures. So I write it here with the I goes to from -2. You have some negative powers that occur more and more in the source and these powers. But the way you solve now this is you solve an homogeneous problem, and then you solve the particular solution. So the particular solution is unique. You just need to resolve what the sources are. And then you have an arbitrary constant for the homogeneous part. But actually, once you solve everything, you solve your algebraic equations, and you find that you can actually fix some further condition on the post-adiabatic solution, and then this constant that was not fixed is fixed, and that's actually what we will need to match the transition motion. We need to be a bit more constraining on the behavior of these quantities, and then the solution is unique. So that we don't have really a justification in Inspiral, but it's just this is what will match the transition motion, and then the solution is unique, and you can do that at every order. And if you do that at every order, you find explicit solution at any order, and we have the explicit scalings of how what the singularity structure of all these equations, and have an interesting structure for even odd n that alternates. And we have extensive checks up to 5 of all this. There are some assumptions because we don't know everything. So we have one assumption that the nonlinear self-force source terms do not diverge more than the other known terms. But I think this is most likely correct. But we are not sure because we cannot compute numerically what the self-force are. But if you have to make those assumptions, then the result is exact to all orders in N. Okay, so that's, let's say, analytically, it is the most we can do. Now, to have the explicit formula, you need to put that into a Tucholsky solver and to a time domain or a Fourier domain time solver. So that's numerical methods, and that we didn't do. So now let's do the analytic work around the transition. So the analytic work around transition now, I want to look in this transition timescale. So the transition timescale, the idea is that when S goes to -infinity, we will join in spiral, and when S is large, we'll go towards the merger. So here is the proper way to write down the parametrization. And so that was the question of Shara. So you have to find the scalings by hand by trying to find where do you get consistent equations and not inconsistent equations. And then you assume that you have an expansion in powers 1/5, because you already have the 1/5 here, and this is the natural thing that appears. If you put additional powers, everything is just 0 in the intermediate powers, and if you don't put them, you find inconsistencies. So, well, that's the way. It's not a proof, but okay, that's the way it works. So now you solve the equations. So the flux balance law, the first one is very, you can directly use it to solve psi. You plug that inside here, it's just given by an integral of the set force. So that will be solved in terms of the set force data. And then, well, you have to plug into the rest of the equations. And then it's a bit long to do. So at 0th order, these are some details of how you obtain this. But you know what? If you are really interested in details, you can ask me questions. But I think I'll just skip the details. The main point is that you can expand everything that depends on the radius in terms of in an expansion. So anything depends on the radius because the radius is monotonically decreasing along the trajectory. So you can use the radius as your time if you want, because everything depends on one variable. It's a one-dimensional problem. So once you know the scaling of your radius, you know radius has some expansion in eta. Well, you can say, okay, I know that my radius has an expansion, so I will do a Taylor expansion of that any function, and I will replace using the expansion of the radius. And then you find an expansion of any quantity. And you only have Taylor coefficients, which are just numbers, and all the unknowns that is the radius at any order. So any quantity you reduce it to just pure numbers, pure number data that you have to determine, and the function that you are trying to solve for. So then everything becomes very easy. You just have for any function, you just need a finite number of coefficients, and you only have equations for your radius. That's the main lesson. So then the leading order equations are these equations. So you have only 3 coefficients, well 4 if you count kappa star. You have four coefficients, and these are the equations that govern your motion. So you mainly have the radius, and you have a couple of equations with respect to the deviation from quasi-circularity. And these 3 equations are consistent with each other. So if you take the first 2 and you take a derivative of that one, by consistency, that one is implied. So they go together. And you can write them in unit normalized form by removing all these coefficients, and then you find this form. And so that equation was not recognized directly by Thorne or subsequently, but actually this is the Painlevé transcendental equation of the first kind. And Quinton Franson, who was a PhD here at K11 and found it was actually exactly that one. And once we know that, it's very interesting because then we know what we are solving. And there's plenty of data that we can use for solving this equation. And then why not? It's just twice the first integral of the Painlevé transcendental equation. So those are known equations. Those are non analytic functions. So you can just plot it something like this. So it has some expansion at early times. It has an expansion at late times. So this is expansion at early times. This is expansion at late times. This one is the plunge. That one will match towards the inspiral. You can, using these properties, you can derive the validity of the transition expansion. I will skip you the details, but it's just a question of knowing what the solution looks like at early and late times. And then you can deduce what's the range of validity, because you want your eta 2/5 R to be less than 1 in these 2 regimes. So that's what gives you the validity. Okay, so that's how you derive the validity. And then once you have the solution, you match. So here is the result from the quasi-circular spiral. Here is the result from the sorry, I put it in the other way. This is the result from the Inspiral. This is the result from the transition. At early times, this is the late Inspiral, and you match them. So you match them. So you see that this coefficient here leading till the 1/2, it's actually exactly matches this one. And it's a bit tricky to do because you have you make two different expansions. So the types of terms that you neglect are different in both ways. But this is the way you do an asymptotic match expansion. You put the two expansions in the regime where they're valid, and then you compare the leading coefficients in each of the expansions. And then after matching the coefficient, well, it just exactly matches. So we did several. One is enough, but we did 4 just to be on the safe side. Now, if you look at the subleading transition motion, this is the results. So everything is algebraic except some differential equations. And these differential equations are linearized Painlevé transcendental equations. And in unit form, they look like this. So it's very nice equations. These first two are the two standard equations, and their compatibility condition is this one, which looks a bit more ugly, but they go together. So they are sourced, and the source depends on the previous orders. So now again, to solve this, you have to solve first the homogeneous problem, and then you have to use the method of variation of constants and solve for the source, so the particular solution. So the homogeneous solution is oscillating. So we found, actually we couldn't find this solution in the literature, probably exists in the math literature, but we had to rederive it. This is the exact form of the series expansion for the linearized Painlevé transcendent that solves this equation homogeneously, and it's oscillating. Since we don't have such kind of association in spiral, we just assume that it is 0, and then that will match the Inspiral. So we just drop the homogeneous solution. We look at the particular solution. Now, the particular solution, we have to understand, so this is the way you write it. You write in terms of the linearized solution with some functions. So this is the standard method of variations of constants. So to solve these p's, you have to make these integrals. You have to know what's the source. And so after the long expressions formed by Lorenzo in Mathematica, and a lot of work to understand the sources, we solve them order by order, etc., and try to see what's the behavior of them. And this is what came up. So this is the behavior of the sources up to I equals 6, where we conjecture is true for any I. And so when we know this kind of expansion for the sources, we just need to know what are the coefficients. So this is what has to be found numerically using some numerical methods. But then we know what's the analytic form. So you need to know how to compute these coefficients using a source which has the form of -t to the power -5k/2, where k is an integer. And so you can actually use this Painlevé exact expression that I derived here to solve for this integral. And this is the result. And then you find some coefficients that you can compute analytically. So then we have an analytical solution. The only thing we need is these coefficients that have to be solved numerically. So then you plug that into the formula, you reconstruct then the solution to each order in I. So you reconstruct the solution in I, and you find the asymptotic solution. And then the magic now arises. So the magic is that this is an expansion with all these expansion. This power is 1/5. So they should take out the radius. It's an expansion with this eta 2/5, which is Orton scaling, and then we made the expansion I over 5 with this function. Now this function, we found what they look like. They look like -t to the power -5k/2 with some coefficients. So we plug that in, and then if you resum this, you can rewrite this in terms of proper time. And when you write this in terms of proper time, you find that you have integer powers of eta in terms of proper time. And so you find this kind of expansion. So it's just rewriting. And so that means that we now can compare this to the Inspiral expansion. So I will just skip that. We can do it for another variable just for cross-check, but one is enough. But if you just now look at the early transition motion and the late Inspiral motion and you compare the two, you find that they exactly match. And this is if the various coefficients match. And we checked around 10 different coefficients exactly analytically, and they match. And we just think that they all match analytically. So because the two expansions simply well, they give you these two results and they exactly match. So we cross-check 10 of them, which is a non-trivial check of these equations, but these are the matching conditions. So I think we got the match. So sorry, I'm 2 minutes late, but here's the conclusion. So we obtained the classification of the radial geodesic motion in exterior Kerr geometry, the ergo region and inner near horizon and near external Kerr. And we obtained a consistent matching between the slow timescale in spiral and the transition motion for point particle orbiting Kerr, including self-force effects. There are many directions for the developments here. Well, at least them here. It's probably a lot to do with these methods. So thank you for your attention.
Okay, let's all thank Geoffrey for a really interesting talk. We have time for questions, so just unmute yourself.
Yeah, maybe I can ask a question. So about this last bullet that you have here, in my mind, I mean, correct me if I'm wrong. In my mind, the EOB is useful. EOB is not a first principles thing, but it's useful because it bridges first principles post-Newtonian calculation with numerical stuff, right? Mm-hmm. In this Emery problem, since you're succeeding in doing stuff analytically, can you imagine that you can do away with EOB completely? That you won't ever need the EOB formalism, which in my mind is just a phenomenological model with enough parameters that you have to calibrate. Maybe that's a bit too harsh, but
yeah, it's probably way too harsh because I mean, yeah. I think it totally makes sense to reformulate it as a one-body problem because this is, by the way, analog from the Newtonian result. I'm not specialist of EOB at all, but I think there's a lot of potential still for understanding EOB more fundamentally. Now the main problem of this formulation of self-force is to compute the self-force, actually. So here I will use everything to just some coefficients, and that looks very simple. But the hard part of the self-force to compute these coefficients, to compute these sources numerically, and to compute the self-force, you need to understand, you have to solve your Einstein's equations. Let me go back to the beginning of the talk, actually. So I'm sorry for this. Yeah. So you have to solve your perturbations to higher and higher order. And so what is known, the state of the art now is to compute H1. So that has been done since many years, but actually since already now to compute H1 for arbitrary orbits in Kerr with inclination and eccentricity it is not optimal because it's very long. It takes very long time, and there are now a lot of methods try to do fast in spirals, fast methods. That is in the development because it's still very, very slow. And there's for the moment only 1 or 2 codes that exist to compute H2, and it has been done only for very specific orbits, like quasi-circular orbits. Or for an eccentric orbit in Schwarzschild. But there are very few methods that are being implemented. There are plenty of numerical problems that appear H2. Nobody has ever computed H3 using self-force methods. And H2 is really a state of the art, and it's it takes a very long time to compute H2. So there's still a lot of possible development there, but compared to the EOB methods that are super efficient at producing waveforms using post-Newtonian data and numerical data, this is very far ahead. These methods will be able to I think at this moment they're complementary, you know, and far less developed than post-Newtonian methods. I would say far less developed.
Yeah, thanks.
I'm curious about this oscillating solution that you mentioned briefly. I mean, it's and you discarded it kind of on physical grounds, but right?
Yeah, yes. So I expect that if you have eccentricity, it will start to become important, because here is a very specific initial condition, the Inspiral. You know, it's a super finely tuned solution. Because you start with exactly zero inclination and eccentricity. But if you relax it and put an arbitrary type of motion, I don't see a reason why all these initial conditions will not trigger all this homogeneous solution. So because you have to match the coefficient of this homogeneous solution have to match with the Inspiral. So if you start with arbitrary initial data for the Inspiral, I guess you will just have to find the coefficient in front of them from the matching. So I think they will appear for the eccentricity and inclination.
So what do they mean physically? What is oscillating here exactly?
It's just the cell force. Well, if you have an arbitrary, so I think for the quasi-circular Inspiral, nothing is really oscillating. But now if you take some eccentricity, there's I don't know. Yeah, the cell force is an integral of over the past Lie cone, you know, of the entire motion. As a function of time, I think it might have a non-monotonic type behavior. It's just, or at some subleading orders, you know. I mean, you can have something that moves. That I mean, even the leading order is monotonic. You might have some subleading non-monotonic CCT, so you can do like little waves because of the potential of Kerr is a bit non-trivial. I don't know. These equations are very nonlinear, I don't have a really fundamental understanding. This has to be understood numerically. So at this point, I don't really know. I just think that maybe since they occur, and I don't see why they should be discarded in the general case, a priori they should appear.
It's interesting if maybe in numerical, like in full numerical simulations, maybe they see something like that. Maybe when the mass ratio is quite large or something. Close to this, I don't know.
So the best would be to have a numerical simulation that allows to decompose the various quantities. If you do this slow timescale expansion, you can simulate independently the subleading variables and see if you approach this code, if you find oscillations or not in these quantities. Yeah, that would be the thing to do.
All right, well, if there are no more questions, then let's thank Geoffrey again in the recording here.